at this one, guys. So you punch these numbers into your calculator. You put your list 1. You put these in list 1. Put these in list 2. Yes.
Yeah.
And you ended up with a mean of what?
1.34.
I'm sorry. 1.34. And it gave you a standard deviation of point what? 0.96. Then how do you find? Then you need to find your variance. Yeah, you square. 0.96 squared. And what did you guys get for that? 0.92.
Yes.
Okay, great. So is he correct? It doesn't really look like it. I mean, it's kind of hard to say. If this is a sample, then it might be off by a little bit, but we're assuming it's the whole distribution. So it sure doesn't seem like he's correct. I would say he's wrong, but it gets a little bit fuzzy. Yeah?
If we write X bar instead
Yeah, the problem is that this is a probability distribution. The calculator called it X bar, so that's an issue with the calculator. It didn't realize that it's a probability distribution, so it should be a mu. And maybe the calculator doesn't know how to do a mu. I'm not really sure. And maybe with a fancy calculator, did yours give a mu? Do you have a fancy calculator or a regular calculator?
Yeah.
Okay. Yeah, that's kind of strange. I don't know. I'm not sure. But it should be a mu because these are probability distributions. So probability distributions should be mu's and sigmas. All right, now we're going to skip on to binomial distribution. So the end of bottom of page 3, I believe, binomial. Yes?
Yeah.
Great. Angela, go ahead and read.
A binomial experiment is a probability experiment that satisfies these requirements. Number 1, has a fixed number of trials. Number 2, each trial has only 2 outcomes. Number 3, the outcomes of each trial must be independent of each other. Number 4, the probability of success must remain the same for each trial.
Perfect. Thank you. So, let's take a look at these. You guys are all writing these down, right? On your notes? We'll take a look at the second one first. The probability has only 2 outcomes. It either is or isn't the trial. So one trial might be flipping a coin. I'll let you guys write. Go ahead and write. I give you guys most of the notes, or else we'd be spinning here and seeing them writing all the time. Okay. All right, so let's take a look. I'm going to start with number 2. So this idea is something happens, a trial happens over and over and over and over again. So, for example, a trial might be flipping a coin. If I flip a coin, does it only have 2 outcomes?
Yes.
Yes, what are they?
Heads and tails.
Heads and tails. So flipping a coin is a valid trial. The thing about it is it has a fixed number of trials. So in other words, you know how many times you're going to flip a coin. I'm going to flip a coin 5 times. That would be one possibility. Or say another outcome that it could be yes or no would be I randomly choose a puppy and it is it's a poodle or it's not a poodle. I can make it into a binomial. Even though there's lots of different kinds of dogs, I can make it into a binomial by making it poodle or not poodle. Does that make sense? There's only 2 possibilities. Either it is or it isn't. If I chose 15 poodles, then that would be my fixed number of trials would be, I know ahead of time I'm only going to pick 15 of them. So the fixed number of trials means you know before you start when you're going to stop. I'm going to do it this many times. I'm going to flip a coin this many times. I'm going to draw a marble this many times. I'm going to select a person this many people, and that's it. Like I said, each trial has to only have two possible outcomes, either it is or it isn't. And then, here's the key thing, the outcomes, also the other things, outcome must be independent of each other, and probabilities have to stay the same. Those are often grouped together as independent and identically distributed. So in other words, the probabilities stay the same each time. If I flip a coin, what's the probability it's heads? 50%. If I flip it again, does the probability stay the same or does it change? It stays the same. So that would be independent and identically distributed. The probabilities would stay the same. You guys remember that one? Independence means the probabilities don't change, they stay the same. So those four things are things you need to sort out. Fixed number of trials, you're going to do it so many times, you know ahead of time when you're going to stop. 2, it only has 2 possible outcomes. Each little trial that you do only has 2 outcomes. And then each of these outcomes have the same probability. They don't change. Here's a question. Rizzo, go ahead and read.
If I have 10 marbles in a bag and 4 are white, and I draw a marble to see if it is white or not, I do not replace the marble and repeat the trial 4 more times. Is this binomial?
Great. So won't you guys take 30 seconds with your neighbors and try to discuss and decide, is this binomial or not? Go ahead. 1 minute.
So it's a fixed number of trials, one more time, it's fine.
The first thing is,
Black or not, white or not.
I don't think so. You're taking, not fixing something. It's not fixing something. There's only 2 outcomes.
We don't know if there's a 3 trials in that.
Or a way.
Black or white.
Yes.
You know,
2 outcomes. Yeah, I don't think that's not like yes. I'm a dog on 5.
yeah, so we don't know. Yeah, if it's only one other solid color, then it would sign for the 2.
So check the core requirements and see if it matches them.
But like white is black, white is black, white is black. Maybe it's like white. Black is black.
Okay, so first question is, I actually like to start with the trial having 2 outcomes. It's the easiest one. Is there something that's done over and over and over again? What's done over and over again? What are you doing over and over again? Drawing a marble. Does that marble only have 2 possible outcomes?
Yep.
Yeah, what is it? White marble or not a white marble? Great, so it satisfies number 2. The first one, are you drawing a marble a fixed number of times? You know ahead of time you're only going to draw X number of times? How many times are you drawing? 1 time plus 4 more. So 5. So it meets the first requirement. Then the last 2 are they independent draws? In other words, do the probabilities stay the same for each draw? No, because once you draw a marble and don't replace it, if I have a marble and I don't replace it, so here's my marbles. I draw a marble and I don't replace it, the probabilities stay the same, the second draw? No, the probabilities change. So if you don't replace it, it changes the probability, so it is not binomial. Now look at the bottom one, the one below it. 15 seconds with your neighbors, talk about that one.
Yeah, I think
Okay, what do you guys think?
yes.
Yes. If you place the marble each time, then the probabilities stay the same each time. Good. Yes? No? Okay. Here's some notation. You should copy those into your notes. We'll get a reader. Eduardo, go ahead and read. Oh, that's little p, by the way. It's little p. One of my classes a few semesters coined it Lil P.
Little peep?
Little p. Go ahead. Yeah, like the rapper.
minus little p equals little q.
Right? If you add them up, they better equal 1 or 100%. Good. Keep going.
So I have to say little n.
No, just n.
Equals the number of trials. X is the number of successes in n trials. And note that x equals 0, 1, 2, 3, until n.
Yeah, x can be any one of those numbers, right? It can be, if I do something n times, I could have 0 successes, all the way up to n successes. They could all be successes, or none of them could be successes. So I can have anywhere from 0 to n successes. Does everyone follow what I'm saying? I flip a coin 10 times, I can have 0 heads. I can have up to 10 heads if I flip it 10 times. So those are all my range of possibilities for my number of successes, my number of heads, or whatever I'm looking for. All right. Who's ever heard of mind your P's and Q's? No one? Really? Never many? I have no idea what it stands for, but I know that P and Q go together. Right? So that's what you get out of this. P's and Q's. P's and Q's go together. So P's and Q's are bonded. If you add them up, they equal 1. They're, does it make sense? They're probabilities that are they complements of each other. But the probabilities of what they are complements of each other. So P and Q always, always, always equals 1 or 100%. Always. If you have P, you can always find Q. If P is 10%, Q must be what? Try it again. If P is 25%, Q must be what? 75%. Good. The other thing that's really important to notice is that P and Q, those are little. The reason why they're little, the probability for just one trial. The probability of just one tiny trial, which is part of the larger thing, right? That's why it's little p and little q, because it's just the probability of just one trial. Good? Yes? Like one flip of the coin and one draw of the marble? All right. So here's the big thing. Do not do this. I should just take that off. I really prefer you guys use this one. It's cleaner. Here is your probability, which goes into your notes, I believe. Probability of getting exactly X successes in N trials. We call that, this is big P, the probability of X is equal to N choose X. Remember that from chapter 3, chapter 4? Times little p to the X times little q to the N minus X. So that before we go much further, I want to point out that the reason why I would prefer you guys to use this is because you've already shown me now, you know how to find N choose X. You've done it on the exam, on exam 1. So now you don't have to show me you know how to do it anymore. You can just use your calculator and find it with your calculator. So let me show you how to do that. Okay, I'm going to turn it on. So let's see, 8 choose 3. How does that sound? So I'm going to type in 8. If I want 8 choose 3, 8. I'm going to go to math. See where the 8's already there? Go to math, the math button. Go over to probability, PRB, probability over here. Arrow over to that. And then if you go down, see where it says NCR right there? That's the one you want. Go down to NCR. Hit enter. And then I want 8 choose what? 3. Type in 3. Enter. Boom. There you go. Good? So again, put in your number first. Math. Probability, down to NCR. So N, and then do that, and then you want put in your X, or whatever your R, whatever your R is. Okay, great. Let's try to understand the formula. First we'll take a look at a tree. So there's a couple. They're going to have 3 kids, 3 children. Each child has a 0.6 chance of being a girl and a 0.4 chance of being a boy. Here is the tree for that. This should be eminently familiar to you guys. The first kid could be either what? Boy or girl. 0.6 chance of girl, 0.4 chance of boy. No matter which branch you choose, because they're independent of each other, the next branch will be either a boy or a girl. 0.4 chance of boy, 0.6 chance of girl. Their third child, same thing. No matter where you are, it could either be a boy or a girl. The 0.4 chance of boy, 0.6 chance of girl. This should be familiar to folks, yes? Okay. How do I find the probabilities? So here, this came from having a girl, then a girl, then a boy, right? Girl, then boy. What's that probability? As you go along a tree, you multiply the branches. 0.6 times 0.6 times 0.4. 0.6 squared times 0.4. 0.6 to the second power times 0.4. Good? This one here, girl, boy, girl. 0.6 times 0.4 times 0.6. 2 0.6s and a 0.4 being multiplied. Good? Everybody on board with this part here? How do I find all these? So remember, this is 40% of 60% of 60% as you multiply. Okay. So, we want to know the probability of having exactly 2 boys out of the 3 children. That makes our success a boy. So, little p is what? So it's 40% chance for boy, 60% chance for girl. So 0.4 for my p would be 0.4, because my success would be having a boy. So it'd be the same as probability of having a boy, 0.4. Which means that q is what? 0.6. That's my probability of failure. My probability of having a girl in this case. So then we're going to look at our formula. And what's our n in this case? How many children am I having altogether? 3. It goes back to this, sorry. You're having 3 children. So I'm having 3 kids. How many successes do I want out of those 3 kids? 2. I want exactly 2 boys. Am I going too fast? Okay. So then what's n minus x? 3 minus 2, that's 1. What does 1 represent? Yeah, the number of girls, the number of failures. I can only do that because I'm a girl. Otherwise, that would be I am. Yeah, I'm really hope none of my colleagues who use my slides are men. And they don't switch that. That'd be trouble. All right. So, all right. So then we have. So really, this n minus x, it really represents how many are failures. Because either you have successes or failures, and you add them up, you better get n. So, you guys follow what I'm saying? If I have 5 kids and I have 2 boys, the rest better be girls, right? So that's how that works. These 2 numbers should have to always add up to n, always. If not, then you've done something wrong. Okay. So for exactly 2 boys, that means my x is 2. We said that's our successes, and n is 3, we said, right? And then outcomes 1 are the ones in purple. So 2 boys, this has 2 boys, boy, boy, girl, boy, girl, boy, and girl, boy, boy. Those are my 3 that have exactly 2 boys. What do those 3 have? What do they have in common? Yeah, they're all 4 squared, 0.4 squared times 0.6. Does everyone see that? Why? Because they all have 2 boys in them, 2.4s in them, and 1 girl, 1.6 in it. So everybody follow where that comes from? Because they're always going to have a girl, a 0.6, and 2 boys, 2.4s. Always. Because they have 2 boys and 1 girl. So that's where this part of the formula comes from. The little p to the x, this is my, oops, wrong one. This is my little p to the x, right there. Little p is 0.4. How many boys do I have? 2. What about then we have the q, 0.6 to the 1 power, because I have 1 girl, 1 failure. So that's where the q to the n minus x comes from. So those two parts of being multiplied in the formula come from the probability of this branch, of having that many successes and that many failures. Everybody all right with that part? So how would I find the probability of having exactly 3 boys? I'd find these and add them up, right? Yes, no? Right, because I can either have boy, boy, girl, or boy, girl, boy, or girl, boy, boy. Or as we add, So this one, or this one, or this one, we add those. But instead of adding them, since they're all exactly the same, everybody see that they're all exactly the same? I just multiply by 3 because there's 3 of them. Does everyone see what I'm saying? So say it was 10%. 10% plus 10% plus 10% is 30%. But since they're all exactly the same, I can just take 10% and multiply by 3 and I get 30%. It's just faster. So all I have to do is multiply by how many there are. How many will there be? I have 3 kids, 3 imaginary children. These are embryos that haven't been determined yet. I am God. How many ways can I pick 2 of them to be boys? I can pick these 2, or these 2, or these 2. I have 3 items. I need to choose 2 of them. Does order matter? No, I'm just choosing 2 of them to be boys. So order doesn't matter. 3 items, choose 2. That's where we get the n choose x from. That's this right there. So that tells us, the n choose x tells me how many branches are going to be there. What is n choose x? Let's see, 3 choose 2. 3 choose 2 is equal to 2 spots, right? 3 times 2, and because it's a C, it's chaos, we divide by 2 times 1, that equals 3. 6 over 2, 3. Good? Yes? Bad? Yes? Okay. So that's where this comes from. So that is my 3 choose, so that's my n choose x. So that's where this comes from, is this times that times that. The first part tells me, no, we'll go back. The first part tells me how many branches I'm going to have that are just that end up with that outcome. And then the next 2 parts tell me the probability of that branch. How many P's I'm going to have and how many Q's I'm going to have as I go along that branch. Say, what if I had 4 kids? Ooh, what if I had 4 kids? Now, there are all of these ways. This one, all of these, all of these end up being spots that have 2 boys and 2 girls in them. 4 kids, how many ways are they getting exactly 2 boys? So what's 4 children? I need to pick 2 of them to be boys, right? So these 4 kids, you 4 embryos, how many ways can I randomly pick 2 of you to be boys? 4, choose 2, right? What's 4 choose 2? What do I have? How many spots am I picking? 2. How many options for the first spot? Next spot? 3. And because order doesn't matter, it's chaos, you're going to have to divide by 2 times 1. So the top is going to be 12, bottom's going to be 2, that's 6. How many of these are there? 6. So that tells you how many branches end up with out of 4 items having 2 successes. Yeah?
On the exam, do you want us to do the tree, or can we just put that into our calculator?
You can just put that into your calculator.
Okay.
I don't need the tree. This is all my explaining to you where this comes from. Which, on the exam, I was all excited the first time I taught this. I thought everyone's like nodding, they're getting it. And then we got to the exam and I put down this extra credit problem and like 1 out of 30 people got it. I was so crushed. So now I expect that you're not going to remember this tomorrow, but that's okay. At least you'll kind of get it now. Yeah.
Can you put on the extra credit and see if I get it?
Maybe, I might do that. I might. I'll consider that. Okay. So again, remember, this is where this comes from. This part is the number of outcomes that have exactly X successes among N trials. And it's how many can I have N items and randomly choose X of them to be successes. And then this is the probability of having exactly X of them be successes and N minus X of them be failures. So you can kind of think about it almost like, saying probability that the first X of them are successes, P times P times P times P, X times, and then the rest of them are failures, Q times Q times Q times Q times Q, however many failures you have. All right. So let's take a look at a couple more notations. So here, I don't know if you have more notes you have to write in on this or not. I can't remember.
Nah.
No? Okay. But again, remember, N is your fixed number of trials. X is the number of successes you have out of those trials. And it can be 0. Don't forget 0. And then P is the probability of success of just one, little p. Little p, probability of success of just one trial. Little q, probability of failure of just that one trial. And then big P, probability of X. That's the probability of getting exactly X successes out of N trials. All right. Here is an example. How about, Adam, go ahead and read for me.
Example, survey on doctor visits. A survey found that 1 out of 5 Americans say he or she has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. My RVX is the number of people in the sample who visited a doctor last month. What is N, what is X, what is P?
Great. So why don't you guys take 30 seconds with your neighbors to try to figure out what's N, the total number of trials you did, what's X, the number of successes you want, and P, the probability of success for just one trial. 30 seconds, or 1 minute, go.
Yes, 10 choose 3.
Okay, what do you guys think? What's my N? Or first of all, what am I doing over and over again? Picking a person and asking them what? If they went to the doctor or not. Okay, so how many times am I doing that? How many times am I picking a person? 10. 10 people are selected.
Set.
Does that, you guys understand that part? Does that make sense now, kind of? I'm selecting 10 people, so that's my N. It's a number of things that you select. Select is the key word there. Select or pick or something along those lines. Or you flip the coin or you do something like that. What's X, my number of successes?
3.
3, exactly 3. I need to find probably that exactly 3. That is my X. What's P?
1 out of 5.
Mm-hmm. 1 out of 5 or 0.2? One out of 5. So here's the deal. I want to point this out at what you should not do because people really want to do this. They want to say P is 3 out of 10. Or 1 out of 10 sometimes, they'll say that. P has nothing to do with N or X. I will say it again. P has, little p has nothing to do with N or X. It occurs before, it's just what the probability is of one trial. What's the probability I flip this coin and get a heads? 50%. Even if I flip it 10 times, what's the probability that I get 3 of them, and I want to find the probability that 3 of them are successes? Still, what's the probability I flip a coin and this one flip is a heads? What'd you say?
1 out of 2.
1 out of 2, 1/2. It's still 50%. This coin flip has nothing to do with how many times I do it or how many successes I want. It's still 50%. It's still 1 out of 2. Are you guys kind of following? So P is already fixed before N and X even come into the picture. So just remember that. Little p, has nothing to do with N and X. It's its own thing. Good? And if you have trouble remembering, try to just remember the P being the coin flip. And then you'll kind of realize it doesn't depend upon N and X. The other thing to think about is even if it did, what's the probability that I have all of them? This is 10. 10 out of 10, that'd be 100%. And that's pretty unlikely that all of them would be anything. Right? So kind of keep that in mind. All right. I know it gets confusing because we've used these things, X's and N's, before in the past in that way, and this is not the same. We're talking about a binomial distribution, so it's different. Okay. So here, we said, before we do that, if my X, what's my Q?
4/5.
Q is what?
4 out of 5.
4 out of 5. If P is 1/5, Q is 4/5. Good? Or 0.2 and 0.8, you can do either one. And then also, what's N minus X? Or my number of failures?
7.
Yep. Everybody good with that part? 10 items, 3 are successes, 7 must be failures. So, here we go. We're just going to focus on this part here. It's going to be NCX, 10 choose 3, times P to the X, X is 3, P to the third, times Q to the N minus X, Q to the 7. So it's going to be 10 choose 3, times 1/5 to the third, times 4/5 to the 7th. Do you guys want to see how I do that in the calculator?
Yeah.
Okay. It's actually not that hard because of how things work. So I want 10 choose 3 first. 10, math, probability, NC3, and 10 choose 3, enter. So then I have 120 there. Then I hit times, and that gives you whatever I had last, my answer. So it's going to be 120 times I want 1/5. So 1/5 is 0.2, or you could even put parentheses 1/5. I can do that. I can do the parentheses 1 divided by 5. That helps better. Raised to the third times failure. You know, I'll do decimals, 'cause that's easier. 120 times 0.2 to the third times 0.8 to the seventh. 0.2013, 0.201. And boom, that's what they have. Yeah.
Do you want us to, like, on the homework on the test, to the third decimal point, to the second?
Yeah, 3 sig figs is good.
Okay.
So 3 sig figs, which means that if you have 0.00004, 4, then I want 3 sig, I want 3 sig figs then. So, we'll talk about that in a minute. Actually, when we'll come up like that. All right, so here's an example. All right, my n is 5, my x is 3, my p is 0.63. So then what's my n minus x? What's that, guys?